A worker pushes horizontally with force F on a heavy crate of mass m to move it up a ramp inclined at angle theta at a constant velocity. The coefficient of kinetic friction between the crate and the ramp is mu k. Part A. On the first dot, which represents the crate, draw and label the forces that are exerted on the crate as it is pushed up the ramp. So, we have the downward force of gravity. We have a normal force that is perpendicular to the ramp, so going off in this direction. It's being pushed up the ramp with an applied force, but that applied force is horizontal. Normally we use Fa for the applied force, but I'm just going to use the F that's given on the figure for this one. And then because it's got friction, the friction is parallel to the ramp and is in the opposite direction of the motion. So if the box is being pushed up the ramp, the friction is directed down the ramp. Okay, so those are the four forces acting on the crate. Part B. On the second dot, draw the x and y components of all the forces without rotating the axes. So if I draw an xy axis, just dotted lines on the original picture, so it looks something like this, with those two angles labeled as theta. When I redraw the free body diagram, I have the horizontal applied force, the downward gravitational force, I have the normal force, which is directed both up and to the left. So I'm going to have an upward arrow and an arrow to the left. Those are the two components of the normal force. The upward arrow, that's the one closest to this angle theta right here. So the upward arrow is going to be Fn cosine theta, and the arrow pointing to the left will be the Fn sine of theta. And I've also got the frictional force to break into components. The frictional force is pointing down and to the left. So I need to make a downward arrow and an arrow to the left. And based on the fact that this angle is theta, the one closest to that angle, the x component, that will get the cosine of theta. So I can label this as FF cosine of theta and label the downward arrow as FF sine theta. So that's all the forces broken into components along the horizontal x and y axis. Part C is basically asking you to do the same thing, but this time to rotate the axes. So now if you turn your paper slightly so that the y-axis is this blue dotted line and the x-axis is this dotted line, then you can see that the normal force and the frictional force are the two forces that are lined up along the rotated axes, and in the meantime, the pushing force, which makes an angle theta, will result in a component up the ramp, which will be F cosine of theta, and a component perpendicular to the ramp but going downward, which is the F sine of theta. So that takes care of this force, but then we also have to break this gravitational force into components. So this angle right here is the same angle theta. So the downward force of gravity will be broken into a component going both along this axis and along this axis. This is the one closest to the angle theta, so that will get the cosine. So we'll have an arrow going this way, which is Fg cosine of theta, and an arrow going this way, which is the Fg sine of theta. So now that all the free body diagrams have been drawn with the axes not rotated and with the axes rotated, see if you can do parts D and E on your own before watching the rest of this video, just to get the practice, because this is a much more heavily mathematical problem than we normally have for homework. So for part D, it says using the force components from part B, which is the second dot, derive an expression for the force the worker needs to exert on the crate to move it up the ramp at a constant velocity. So since it's moving at a constant velocity, that means the forces are balanced. So we can say the net force in the x direction is equal to 0. Forces are balanced that way, horizontally, and the net force in the y direction is equal to 0. If you look in the x direction in this diagram, you're going to equate the rightward forces with the leftward forces. So it's going to be F on the right side is equal to the sum of these two forces, Fn sine theta and Ff cosine theta, on the left side. So we'll just write that down. F equals Fn sine theta plus Ff cosine of theta. And the next step is to plug in any formulas that you may know. And so we don't have a formula for the applied force or for the normal force, so we'll leave all that part of the equation just as it is. But we do have an equation for the kinetic frictional force, which is mu k Fn and then times the cosine of theta. So all I did right now is I just replaced this frictional force with the equation for the frictional force right there. And that's as far as we can go on that side for now. So let's look at now doing the y direction. So in the y direction, we're going to equate the upward forces with the downward forces. So we're going to set Fn cosine of theta, Fn cosine theta, the upward force, is equal to the sum of the downward forces, the Ff sine theta and the Fg. So we have Ff sine theta plus Fg. And just as we did with the x direction, the next step is just to rewrite this equation but plug in any formulas we may know. So we have Fn cosine theta is equal to mu k Fn sine theta plus mg, the gravitational force. Alright, so let's look at what we can do now to simplify all this. We are trying to find the F, the applied force, this term right here, which also shows up actually nowhere else. So we just need to solve for this F. But we have one other unknown variable, which is the Fn. That shows up right here, and right here, and right here, and right here. So we need to find a way to get the Fn by itself in this other equation, and then plug it into this first equation. But to make things a little simpler, because we have multiple Fn terms, let's just factor them out. So going back to the Newton's first law in the x direction, we can write the next step as F is equal to, let's factor out the Fn and leave this as sine theta plus mu k cosine theta. And on the other side, we're going to bring this term with the Fn over to the left side of the equation. So we're going to subtract it and factor out the Fn at the same time. So Fn, and then what's left will be cosine of theta minus mu k sine of theta, and all that is going to be equal to mg. Now the final step over on this equation is to just divide both sides by all that stuff in parentheses. So Fn will be equal to mg divided by and then everything that was in parentheses, which I no longer need to keep the parentheses on, cosine theta minus mu k sine theta. And if we take this whole equation for Fn, we can plug it in to this one right here, and what you end up with is F is equal to mg over the cosine of theta minus mu k sine of theta. So that's all of the Fn from over here, and then we just have to multiply it by all that part in parentheses. So that is going to be the sine of theta plus mu k cosine theta. And all of this is basically just the answer. It's written in a slightly different form on the homework sheet, but it's the same thing. So that's the answer to part D. A lot of math in that question. For students in AP Physics 1, you would most likely not have to go all the way through with this question. You would probably stop around coming up with this equation and this equation, and that would be far enough. For students in AP Physics C, you would most likely have to go all the way to the end to get the final answer. So, now that you've seen that one work, I would like you to try part E completely on your own to see if you can do the same thing. I'm going to kind of work through this one a little bit quicker now. So, we'll start with the x direction, which is now this is going to be the x direction, and this will be the y direction. So, we're going to start with the sum of the forces in the x direction equals 0, and the sum of the forces in the y direction equals 0. In the x direction, if we equate the two sides, this is equal to the sum of these two. So that'll be f cosine of theta is equal to ff plus fg sine of theta. And if I plug in some formulas, that gives you f cosine theta is equal to mu s or mu k fn plus mg sine theta. And for the y direction, we're going to equate the upward force, the Fn, equal to the downward forces, F sine of theta plus Fg cosine theta. And let's plug some formulas into this one too. So Fn is equal to F sine of theta plus, and the only formula we can plug in over here is the mg. So mg cosine of theta. So let's do the same thing as before. Let's solve one equation for the Fn, the unknown, and then plug it into the other equation. Well, this equation has already got the Fn by itself, so let's just take this equation for Fn and just plug it in right over here and see what we end up with. So we have F cosine of theta equals mu k. Now in place of the Fn, we're going to put everything from the equation over here in place of this Fn. So that will look like, in parentheses, F sine of theta plus mg cosine of theta. And I've got to keep going, so I need to erase off. I'm not able to erase that line. So, since it's not letting me erase that line, I'm just going to have to write over it. So we have that part, and then we have to include this last term as well. So that'll be plus the mg sine of theta. So The rest of this is just pure math now. And since I don't want to keep going with this video because I don't want to walk you through everything, I would like you to try to solve the rest of this on your own. You're going to distribute the mu k into the parentheses, so it multiplies on both of those terms. Then you need to get the two f terms, the two terms containing the f, on one side of the equation together. And when you factor out that f and divide by everything else, you should end up with this exact same equation that you got in part D.